OOM. Welcome to OOM's Fridays, our Fridays. It's very, vou falar inglês para os colegas poderem entender. It's an honor to have you all here. It's very important for us as a small institute to be able to welcome scientists from overseas and from the outside, give young scientists a new perspective on what can we do with science, with open science, with different points of view. It is very important for the training. Of course, we have the participation of the university, but we are not inside the university, so it's very important for us to have these different perspectives. And I think I would like to thank my colleagues for coming. It's very rewarding to see an audience so well composed in these events. It's very, I try to convince them that it's also very important to come to these events that we have, so that they can learn as much as they can. And just I'd like to thank you for coming and ask Manfred to introduce you and to introduce us how you met and how this came about.
I actually don't remember well how we met, but he phoned me last year after summer or something, and told me Ralf Schiebel is from Max Planck Institute of Chemistry in Mainz in Germany. His academic background is his name is he's a geologist and working with small planktonic organisms mainly, I guess, foraminifers, and trying to look back for paleoclimatic issues. So we met many years ago after a cruise. He stopped in Funchal with Poseidon, and so we met, and he called me then, told me the whole thing about this a sailing ship built for purpose for research. So, and I'm quite happy to have him here, and together with his colleagues and skipper also present, and introducing, presenting this very nice yacht.
Jetzt geht's. So, first of all, I want to thank Rücker and Manfred Kaufmann for inviting me to give a presentation to you today. I'm very happy to be here and to show you our project. I don't exactly remember, we should have met in Kiel where we were students at the same time, but we didn't know of each other, and you always meet twice, in life. And now finally we made it happen for me to come here to your place and to the presentation which I always wanted to do. I was sailing this area very often with the larger research vessels, meteoring with Poseidon, and sometimes we had a short paragraph in your local newspapers about our research, and now I'm really very happy to meet you all and to be here. So we are now in the Marina da Quinta del Rode, our research vessel, Eugen Seibold, which you can see here. And we are actually from here. You can see that we have a flag from Portugal and we are registered in Madeira. So special thanks to Calorial, to Joanna, Anya and Paulo Camacho from the International Shipping Registration of Madeira. So it was actually not very easy to get a place with a good flag for our ship, because we are really small. And when we started this project about 5 years ago, and we started thinking about having a research vessel, we did not expect to have so many problems. So when you build a ship, it's not only technology. You need to find a shipyard who builds the ship, but then you have a lot of administrative things to do as well. So, for example, you have to find a flag, and we could not register in Germany, because in Germany we would need 6 captains on board at all times, because we would have 3 shifts of 8 hours, and at each shift we should have 2 captains. So in Germany that is impossible to have. So now we are sailing with you, and we feel like part of you. We are really happy to be under your flag, which solved a big problem. So without Madeira, it would not be possible. So then we needed to find, of course, money for the ship, and that's the Werner Siemens Foundation from Switzerland who gave us money. this Siemens Foundation is supporting a lot of science, and each of you can, when you have a big project, ask for money there. Make it big, so ask for many millions, and then I think about giving it. They do not support small things, they support big things. So they gave us 3.5 millions, which is usually not enough for such a big ship. A big ship like that costs typically 7 million euros. So we luckily found a shipbuilder who just retired. He had a big shipyard in Germany, and he retired and he was bored. So he said, well, I will do a ship for that price. That was great luck. And then we found a retired ship's designer, Lorenzo Argento from Milano in Italy, and he did the design basically for free. So we saved a lot of money on that. So then we found a great shipping company, Leis from Hamburg, and they run also bigger research vessels in Germany, like Polarstern. It's a big German icebreaker, and we are in the same shipping company. So they are very experienced, and they run our ship. So now I come to my talk, but before I do my talk, I want to about sailing the ocean for climate geochemistry. I want to introduce you some more people from our department of climate geochemistry, which is only 3.5 years old. So we started a new department in Mainz. Head of the department is Gerald Rauch, this guy here, who did finally get the funding. So we started it all, we wrote the proposals, and the Werner Siemens Foundation gave money to him. And Jens Egler is our head of administration, and he helped us a lot with finding your flag, for example, and getting it all running. And then we have found two great scientists, Eliana, who's sitting here from the Netherlands, and Maria Calleja from Spain, who's sitting here, who do the research on the vessel together with me and a new colleague, also from the Netherlands, who will start next Monday. So now is really the start of the project. We sailed here from Lanzarote last week to test all equipment, and from now on we will do the science. And this presentation is also a request for you to participate. So if you have interest in doing science with us, if you want to share samples, if you want to sail with us, please approach us, and we will make it happen. So then we have a great crew from Estonia. Karel, Kruzmegi, the captain, who's sitting here, he's a very experienced sailor. And Argo and Janet, these three are running the ship. And of course, this small crew and scientists is not all we have. We have many technicians in Mainz with a big workshop. So many people are involved in this project. So finally, I will present you now a little bit about climate change. Then I will introduce you to these organisms, which are planktic foraminifera. And in these planktic foraminifera and the different species, which make the species assemblage, from this we will reconstruct, or we do reconstruct climate. So these foraminifera are made from calcite, calcium carbonate, which affects climate and which is affected by climate, for example, ocean pH. I will show you in a bit. And then we do a lot of chemical analysis at home in Mainz at our laboratory. For example, we can analyze cation to calcite ratios, for example, magnesium-calcium ratios. And this here, so this is not pure calcium carbonate, a little bit of magnesium is also here. And this ratio gives you a very good paleo temperature. So 1 million years ago, we can of course not put a thermometer in the ocean and test or probe temperature. We need to reconstruct it. And we do it with these the chemical composition of the foraminiferas. We also use a lot of stable isotopes like carbon, oxygen, and nitrogen isotopes to reconstruct not only temperature but pH, CO2 concentration, a lot of things, paleoproductivity. So, having said that, I have split my presentation in 3 parts. I will talk about climate change, if it's real, why, how, when, and where. Then we'll talk about microplankton in general and planktic foraminiferas in particular. And then I will show you some slides about our Eugen Seibold research vessel and what kind of technology we have in the boat. So as I said, climate change is not something which is new. So this article here, for example, describes that the furnaces of the world are now burning about 2 billion tons of coal a year. When this is burned, uniting with oxygen, it adds about 7 billion tons of carbon dioxide to the atmosphere yearly. this tends to make the air a more effective blanket for the Earth to raise its temperature. The effect may be considerable in a few centuries. When you read this, it could be a modern newspaper article. This is actually not new. So this was published in a newspaper of New Zealand on the 14th August of 1912, more than 100 years ago. And the numbers we know today are not much different. So today we know that it's about 3 billion tons, and they were talking about 2 billion tons. So the order of magnitude is the same, and that was known. So that was a publication by Francis Molena, and he just copied the information given by Svante Arrhenius, who was a great geologist some time ago. So climate change is not new, we knew what would happen. And then I found on the internet now some information of Madeira. And in Madeira, climate change is not really very evident, not as evident as in other parts of the world. But still you can see that from about 1973 to today, here is 2017, day temperatures were rising a bit, and also night temperatures are on the rise. So maybe you felt it, maybe you didn't. Usually when you talk to farmers or when I give presentation to wine growers, they tell me, yes, we know that climate is changing because now in northern Germany we can grow wine which we could not do before. Maybe Madeira got drier, maybe it got wetter, but something must have changed here as well. So climate change in your place, you live in paradise here, really is not very strong, but it is there. When you look, for example, at Europe, you can see that climate change is much stronger. So what I show you here are the number of tropical nights, which are night temperatures over 20 degrees Celsius, because it makes you sleep bad. And you can see here, this is the place where we live now in Mainz, and there are almost no tropical nights per year. So this is in the period from 1961 to 1990, and you can see here towards the south there are tropical nights, very warm nights. But now look at what happened. Now we have already in mind some tropical nights. So the temperature, the night temperatures are rising in Germany, and you will see here that in the very near future, from 2071 to about 2100, we will have many tropical nights in Germany, but many more in the Mediterranean region. And that makes life uncomfortable. That makes not only temperatures higher, it also makes the atmosphere drier. And that's a big problem, really, for humans. That is a publication from one of our colleagues at Max Planck from 2016 about the Near East. And climate is also always affecting civilizations. So no wonder that in some parts of the world we have wars, because life gets more problematic. You cannot grow your food as good as before. You have a lack of water. Of course, in the Near East, it's also the American want for oil. It's very political. But also climate affects societies and affects migration. So climate always changes. Now we think we have a large effect. We know that we have a large effect of us burning our fossil fuels because we are increasing the CO2 concentration of the atmosphere. But when you look here, we have over the past history, and these are hundreds of millimeters of precipitation, we have climate change. So here we are today, and we can see that we had for a couple of hundred years something which is called the Little Ice Age. The Little Ice Age started at about 1600, and climate in Europe got colder. At the very end of this Little Ice Age, we have the French Revolution. It was really cold in Europe, and people could not grow enough food to have enough alimentation. So people made revolutions because climate was so bad, the crops didn't grow anymore. Today we are in a rather warm climate. Before this Little Ice Age, we had the medieval warm period. I can show you a picture of this Little Ice Age actually here. So this is a typical painting from a Dutch Breughel, Dutch painter, and during this Little Ice Age, people in the Netherlands, the artists, painted a lot of these winter scenes because the winters were long and very strong. They were very impressive. In the medieval warm period, things were completely different just before. So in this period of time, between about 800 and 1500, climate was warm in Europe. Greenland was discovered by the Vikings, because climate was warmer than today. So when we look further back in time, we can see here ice ages and warm ages. So what we have here is a climate curve. And this climate curve starts here today. We have a warm climate, an interglacial today. And about 20,000 years ago, we had the last glacial maximum. So the maximum glaciation 20,000 years ago. And then we go back another 100,000 years at about 130,000 years before today. So these are numbers in hundreds of thousands of years. We had the last interglacial maximum, a warm period, and before that we had a cold period. And you can see that these glacials and interglacials are periodically. It's warming up rapidly, and then it's cooling down slowly, and it's warming up rapidly, and then it should cool down slowly now, but it will not do, because now the atmosphere is full of CO2, and what you see here is that these temperatures, which are reconstructed from benthic foraminifera, stable oxygen isotopes, so that's a chemistry of benthic small calcareous organisms. This temperature correlates very well to CO2 concentration. So here you see you have a lot of CO2 in the atmosphere, you have a high temperature at the global scale, you have little CO2 in the atmosphere, you have a cold temperature. That's a greenhouse gas. So you can see here that the typical interglacial concentration of CO2 in the atmosphere is about 280 parts per million, ppm. And the typical interglacial concentration is about 180 ppm. So CO2 is not the only greenhouse gas. We also have, for example, methane here and nitrous oxide. So we have many greenhouse gases. But also methane and nitrous oxides are produced by us, for example, by farming. Farming produces a lot of methane. Rice farming, cattle farming produces a lot of methane. So that is the background. So today we are here, we can see that this is a natural background, maximum between warm periods and cold periods. Today, and this publication is some time ago, that was published when the atmospheric CO2 concentration was 370 ppm. So this increase in CO2 can only be explained by human fossil fuel burning. It cannot be explained in another way. Today we are actually over 400, so today we are sitting about here, much higher. So we can see this here. This is a natural background of a warm interglacial period, and this is an increase we have done as humans over the past 150 years. We call this the hockey stick curve, like a hockey stick, going in the same way for a long time and then increasing rapidly over a very short period of time. So that's what we do now. So this is something very interesting actually. This is called the Holocene. This is our interglacial period in which we live now. This is again the last glacial maximum. And we can see here that over the past about, let's say, 80,000 years, we have many rapid climate changes in the northern hemisphere. So these are data from ice cores from Greenland, Grip and Gisp, and this is an ice core from Antarctica. And we can see that in the northern hemisphere we have many periods of very rapid climate change. Again, warming very rapid and cooling a bit slower. And this could happen to us today. So when we increase CO2 a bit further, this is not entirely comparable because this was a different baseline. But we can see that climate change can be very rapid over maybe 10 or 20 years, and then we have a much warmer climate, and then it's cooling down a bit slower. But if that happens, we will have a real problem on Earth with crop farming, with glacier melting and all of these things. And we can see that, for example, Antarctica was not affected in the same way. We call it the bipolar seesaw. So the climate of the two hemispheres, northern hemisphere and southern hemisphere, is affecting each other, but is not completely the same. It's a very complicated system, and we try to understand it better. I show you how in a bit. So again, this is a hockey stick curve. This is year 1000. We leave the warm period, and about here, industrialization, starting in England and then Europe, this enormous increase to about 410 ppm of CO2 in 2018. And here we have a period of recording CO2. This is from the Mauna Loa Observatory on Hawaii. And people started there in 1950 about to measure CO2 in the atmosphere. And you can see that it's constantly rising. The small peaks in here, these are the northern hemisphere winters, in which CO2 is a bit higher, and during summer, most of the land vegetation is consuming a lot of CO2 and producing more oxygen. The CO2 concentration is a bit lower. So you can see here these wiggles, but on a long-term trend, CO2 is increasing, and that must lead, there's no other way, to an increase in global temperature, and people now talk about 1.5 degrees Celsius to limit it, but that's impossible. So we will have very soon an about 2.5 degrees Celsius increase in global temperatures. So now I go back a little bit in time again. Over the past 5 million years, we can see this glacial, interglacial periods with warmer climates and colder climates. And this actually here, about 2.7 million years ago, is the start of our quaternary period of time, the ice ages. And before that, we had a much warmer climate, which is called the Pliocene warmth. So here, before 2.7 million years ago, the climate was much more balanced and much more warmer. And you can see going down here that the amplitude is much higher now. So the cold periods are much colder, and the warm periods are about the same temperature as this Pliocene warmth. So that's what happens to climate at the natural scale. Here we have a look over the past 70 million years, and we can see that here we have dinosaurs on Earth. That's the end of the Cretaceous period. And then we come into the Cenozoic, and we can see here a very warm climate. Actually, with this very high peak, with this very warm climate, that was caused by methane. That was a methane outburst. We can measure that by stable isotopes. So at this point of time, also India collided with Asia. So the subcontinent of India drifted into Asia. Here we have the opening of the Drake Passage between South America and Antarctica, and we can see here when Antarctica was separated from South America, Antarctica started to glaciate. From about here in the Miocene, about 15 million years ago, we had the start of the Northern Hemisphere glaciation. And here at about 4 million years ago, we had the Panama closure, when North America and South America grew together at Panama, and circulation between the Atlantic Ocean and the Pacific Ocean was stopped. That created the Gulf Stream, the North Atlantic Current, which brings the warm climate to Madeira, but also to Northern Europe, but which also brings a lot of humidity to the North Atlantic, which led to the glaciation of Greenland. So that's normal. That is very often caused by tectonic events, like the opening of passages or the closing of passages. And here we see we had a very warm climate, about 6 degrees warmer, some 50 million years ago. So now, when we plot, so here you can see again the ppm of CO2, 2000 ppm of CO2 in the atmosphere makes a very warm climate. So our anthropogenesis peak, if we continue burning fossil fuels, we will have at least 1800 ppm, which is very similar to this point of time here. If we get even worse, we might end up with 5,000 gigatons of carbon burning per year. So when we then plot this hockey stick curve into this long-term trend, we will see that here we are today. If we continue burning our fossil fuel, we will end up at the same conditions we had on Earth 50 million years ago. Bangladesh or the Netherlands, they will have a real problem. So most of the cities which are built close to the sea need to be evacuated, and people have to move up higher. So that is the background. So that is our purpose. We want to better reconstruct and better understand past climate change, because past climate change teaches us a lot about modern climate and about modern climate change. So now I will present you how we do it. We do it by analyzing microplankton, including these planktic foraminifers. And we call these tools our proxies. I will show you how that works. So this is a plankton in the ocean. So we know very well the global biomass of plankton in the ocean. We have different plankton living in the ocean. For example, here we have the picophytoplankton, which are basically bacteria. They make a big biomass in the oceans because they're extremely numerous. So when you jump into the water, you are surrounded by bacteria. Don't be afraid, because you are full of bacteria yourselves. So we have other bacteria sitting here. Then we have diatoms. Diatoms are making the ocean green. So when you look onto the ocean in spring, it's getting green. This is a typical plankton algae, which are diatoms. And here we have the foraminifers, which make a very, very small portion only. So when we analyze these foraminifera, we know that they did not really affect the environment, but they did record the environment, which is really beautiful. So that is the best you can get. If you measure temperature with a small thermometer, which will not change the temperature of your bathtub, it's very good. If you would have a very big thermometer, it would empty the bathtub and would make it colder. So we have a very small thermometer, but which measures the temperature in a very good way. And here we have the coccolithophores, and coccolithophores are a bit more important, and they are also wonderful proxies for reconstructing climate change. So both of these organisms here have calcareous shells made of calcite. Here you can see the diatoms. When you have them under the microscopes, they are really beautiful. These are made of silicate, SiO2, so they are not calcareous, they are silicious, as well as the radiolarians, another group of beautiful animals. So these are plants, actually these are animals under the electron microscope, very beautiful, so they are contributing to the plankton. Here you have coccolithophores. This is the most abundant coccolithophore in the ocean today. It's Emiliania huxleyi, and here you can see the scale. So these platelets are about 2 to 3 millimeters in diameter. So inside of this sphere we have a living plant cell which is surrounded by these calcite platelets. And then we have dinoflagellates. I put this here for Manfred because he knows them well. These dinoflagellates are also producers, but are also consumers. So dinoflagellates are special because they are plants and animals. So they have chlorophyll, they produce biomass, but they also consume biomass because they can eat. The dinoflagellates. So now we come to the foraminifers. So here you can see a foraminifer shell. This is a very special species which is round like a very little golf ball. The diameter is about 0.5 millimeter, and you can see that this foraminifer is surrounded by symbionts. So very small algae are sitting here around this foraminifer. It has long spines and cytoplasm, and these symbionts support the foraminifer with oxygen. So they consume CO2 and produce oxygen. And when these foraminifers form their calcareous shells, they also consume calcium carbonate. And when they die and sink to the ocean floor to form the deep ocean sediments, they form calcareous sediments. So these foraminifers, they live in the surface ocean. In the surface ocean. Here we have maybe the upper 70 meters of the ocean, and here we have a green band, which we call the deep chlorophyll maximum. So when you dive down in the ocean, you have a very warm surface and a cold deep, and this temperature change here causes also a gradient in density, and at this gradient a lot of the empty or dead tissues of plankton get stuck. So this layer down here is very green. When you take a sample from the ocean water, you can see in your sampling bottle it's green. So the foraminifers give birth here, so these are small foraminifers. Then during their lifetime they move up in the water column, they are washed up by currents, and when they get big and mature to reproduce, they go down here to the deep chlorophyll maximum. This is one group of foraminifers, about 50 species in the ocean today, which is very little. It's very easy to learn them for us, to do the climate work with them. And then we've got about 5 species which are living in the deep ocean. So when we now catch these species and we compare their chemistry we can make very good estimates about the strength of the pycnocline here. So we can compare the deep ocean conditions with the surface ocean conditions, which is very beautiful. And these species live between the tropical ocean and between the polar ocean. And their average lifetime is about 1 month. And most of these species do reproduction at full moon. So next time when you see the full moon in the sky, think about foraminifers. There's a lot of things going on in the ocean, just in front of you. So, we have a very good data set today. So I sampled the ocean for about 30 years. So most of my research was done in the North Atlantic Ocean, and I came to Madeira, as I said before, very often. So we've got a very good data set in the North Atlantic Ocean, in the Caribbean, in the Eastern North Pacific. I sailed a lot in the Red Sea and the Arabian Sea and the Indian Ocean around Japan. And then when I did my work in France, I did a lot of cruises with a big research vessel called Marion Dufresne to the Kerguelen Islands to sample the southern Indian Ocean. So that's our data set, which we want to improve. And from analyzing all of these data, we know that these foraminifers and the coprolithophores, which are living in the surface ocean, make a big contribution to the overall calcium carbonate production in the open ocean. And here you can see that about 80% of the deep sea floor is made by foraminiferous shells. So when we take a sample from the sediments, from the deep sea mud, we have mainly foraminifers in our hands. Above a line which is called the calcite carbonate depth, when we go very deep into the ocean, all of the calcite is dissolved, and what is then left over from the calcium carbonate are mostly coprolithophores. So they are really important for calcite production in the deep ocean, these foraminifers. Oops. And we can see that we have tropical assemblages in the tropical ocean, and when we go further towards the poles, we have a change in our assemblages. And then we have something here off Western Africa, which is called upwelling. Deep waters are coming to the surface of the ocean to increase productivity, and in these areas, here, for example, also of South America in the Arabian Sea, we have a different assemblage. So we can very well reconstruct latitudinal bands, but also special ecological conditions. So here again are these different 50 species, which we know very well for their average temperature and their average abundance. So we can really, in very much detail, reconstruct each region of the ocean with our foraminifers. And we can do that at least over the past 70 million years in a very good way. So here we can see, for example, that when we had the big extinction of the dinosaurs, maybe you heard about it, at the end of the Cretaceous, we had also a big extinction of foraminifers. We had large foraminifers in the ocean, so this is a size between 0.3 and 0.6 millimeters. And most of these species got extinct, and then we had a new group of species which made a big evolution over time, and that is related to climate change. So I showed you this curve in a horizontal way before, so this again is climate change. Opening of the Drake Passage, cold climates here, and then opening of the closing of the Panama Isthmus and very cold climates here. So we can relate our species evolution and the size of the species to climate change. The blue colors are the polar species and the red colors are the tropical species. And we can see that species grew bigger when climate became colder. So when climate is now getting warmer again, we will have smaller species, less calcite will be produced, and less of the CO2, which is in the atmosphere, will be consumed by the plankton. So there is a threshold. When we overshoot a certain threshold of CO2, we might have an extinction of this plankton, which is very, very dangerous, because the ocean will consume less of the CO2 and the atmospheric CO2 concentration will rise much, much faster than it does now. So, surface ocean and surface world systems are not linear. Be careful. Sometimes you have a very rapid change when you change the overall parameters of your environment. So this is how foraminifers look like under the scanning electron microscope. They start small and they add a chamber, or maybe many chambers per day. When they grow bigger, they add maybe only one chamber per day. And after 1 month of growth, they are big, and then they can reproduce and have their babies again. So this is the opening out of which the living animal goes to the outside to harvest the symbionts around, and these here, the small dots, are pores, and these pores allow oxygen exchange to supply the mitochondria at the inside with power. So here we were lucky to crack one of these forams open, and there you can see the little baby foram lying inside of the mother shell of a bigatist. So then I come back again here to chemistry again. Very shortly, now I want to present you what we do at the laboratory at home in mines. So we look here at ultrastructures. So we analyze, for example, this species here. And what we have at mines is a laser ICP-MS. So we have a laser shooting into a foraminifer. This is a different species. So this is about 50 micrometers in size, 0.05 millimeters big. So we shoot into the calcite of the foraminifer to get calcite material out of it. And this calcite is then pumped into a mass spectrometer. And with this mass spectrometer we can measure stable isotopes and element ratios. So, for example, what you can see here is a change from this laser ICP-MS in magnesium-calcium concentrations. So this is the inside. We usually shoot from the inside of a broken shell, and we can see here that we have high peaks and lower minima of magnesium-calcium concentrations in our shell. That's a different shoot here. So we shoot from the inside to the outside, and we ablate a lot of calcite. Layer by layer, we take the calcite off the shell and analyze it. And what we can see is that we have a layered structure of magnesium-calcium changes, and this here is a different methodology that is so-called nanosims. And with the nanosims, you can make images of the same shell broken open here, and we can see with this nanosims that we have here the primary organic membrane, which is sitting here, which is organic, and from this membrane the calcite grows to form the shell. And the calcite grows to the inside and to the outside. And what we see here is changes also in magnesium-calcium. Here are magnesium-rich layers in this calcite shell. So the scale is here 25 micrometers, and the resolution of this nanosims machine is about 100 nanometers. 100 nanometers, very small. So we can see here bands of high magnesium calcite and low magnesium calcite. Here you have the scale, and these are day and night bands. So what we can do also with foraminifera from the Cretaceous, 100 million years old, we can reconstruct day and night temperatures in the ocean. So when people like Trump say there's no climate change and we know nothing, and we say, well, I mean, we can say your day and night temperature of Madeira, if it would have been there, which is, it was not 100 million years ago, yeah, it's very sad. So we think we know very well what's going on, and we get better and better. But we need more samples, and we still need to understand more proxies. So that is the analysis of calcite. But what we also can do is the analysis of the organic linings between the calcite layers. So I go back here. So between each of these layers we have a very thin layer of organic matter. And in this organic matter we have nitrogen. We can see here the organic matter. Here we dissolved in this foraminifer the calcite using acids. What is left over is an organic lining, which is very, very fine. And from these organic linings, we can analyze nitrogen isotopes. And nitrogen isotopes give us a very good guess of the paleoproductivity. which is very important. So productivity of the ocean is important to consume CO2 and to produce oxygen. So what we have done here over the past 160,000 years from different areas, subarctic Pacific Ocean, subarctic Atlantic, California margin, Caribbean Sea, South China Sea, and this is an average climate curve. We have analyzed the nitrogen to understand the regional paleoproductivity. So here you can see, for example, there's a big, in this period of time, difference in paleoproductivity between the Caribbean Sea and between the South China Sea. On average, you can see that paleoproductivity follows glacial and interglacial cycles. Here again, last glacial maximum and our interglacial today. So on average, we have the same pattern, which is very good, but at the regional scale, we have big differences. So that is one of our specialities in Mainz today. We have built a very big laboratory to analyze nitrogen isotopes from very, very small amounts of matter. From one foraminifer, from one big benthic foraminifer, we can now analyze nitrogen isotopes. And it's only Princeton University in the US and Mainz who can do it today. So if you have a good idea about your samples or your projects, you are very warmly invited to measure the nitrogen isotopes with us. So what we have learned is that marine plankton does affect and is affected by climate. For example, changes in CO2, temperature, pH, oxygen, nutrients, and the availability of food. Very important. And all of these parameters are recorded by the assemblage and chemical composition of plankton fossils and allow a reconstruction of climate change and a more systematical and quantitative understanding of climate. So now we come to the sailboat in a bit. So typically we do our research with these big research vessels. This is Maria Sibylla Merian, a German research icebreaker. And this is Reykjavik, and I did an expedition with this vessel in 2016 to the North Atlantic, and our expedition finally ended in Ponta Delgada after 6 weeks. So here you can see a plankton net, a big steel case with an inlet here, and we let it down in the water column, and when we get it up, water is going into here, and the plankton samples are then down here in the sampling cups. This is a rosette of water samplers. So this we get down into the ocean, and when we get it up, we close bottle by bottle by bottle, and we have water samples of the entire water column. So these research vessels are great. You need a planning which takes about 2 to 3 years before. So we know that we will go to the ocean in 2 years, if we are lucky, and this vessel costs 60,000 euros per day. So our idea was now, and these vessels of course have a diesel engine and they burn fossil fuel. So what we do now is Eugen Seibold, and this is our new research vessel, which was baptized last year in Kiel. So I put this also for Manfred, because Manfred was a student here at the Institute for Marine Sciences in Kiel. And our sailboat is named after Eugen Seibold, and he was the founding father of modern marine geology in Germany in the 1960s. And he was born on the 11th of May 1918, and except on that day, 100 years later, we baptized our ship to this name. So, this is what we did yesterday. You know this place in the background, this is Madeira. So when we came here 3 days ago, we did the first trials with our plankton net. So this is the same plankton net as you saw before on the large vessel, but this one we built at the Max Planck Institute from titanium. This is very lightweight. It only weighs, this case weighs only 40 kilos, and the steel net weighs 120 kilos. So we needed a light net to use it on the ship. This is a large volume pump with which we can pump ocean water to get our plankton samples on filters, which we can then analyze. What we have here on the ship is an A-frame. So this frame we can get into the ship to attach our sampling gear, and then we put it out, and then we can get it down with this line. This is a 6mm Dyneema rope, which is very strong, and which we get down into the ocean. So this is our working deck. This is Heidi Adler sitting there, and this is Maria Pareja. and this yellow head, that is my head. So we get our sampling gear down here with our research vessel into the ocean. At the same time, we pump water through the keel, so we have a keel with a tube inside into our laboratory here. So we analyze water from 3.2 meters depth in the laboratory here for everything we can do, temperature, salinity, chlorophyll, turbidity, pH, CO2, everything. And then we have on the boat a large snorkel, which we might see a little bit later, to pump air into the air laboratory on the other side of the ship to analyze the CO2 from the air from 10 meters height above the ship. So that is towed sampling. I show you now a little video. So this is in the background, this is the island of Fuerteventura. We are now based typically on Lanzarote. So here we have a bongo net coming back onto the ship with the first samples we got. So that is the wind, which you can hear in the background. It was a very nice day for sampling. So when we have these nets behind the ship, they work as a floating anchor, and the ship is floating in front, so they are nicely drifting through the same water body, and we get perfect samples. So that is a bongo net for plankton sampling. And here we get our water sampler rosette back, which we need to catch. So here you can see the water bottles, and in this water sampler we also have a CTD, which is a device that records depth, temperature, salinity, chlorophyll, pH, etc. So that's what we did over the past 2 weeks. So our boat is now ready to be run, and here you can see a very nice device which is called a ferry box. It's called a ferry box because these devices were put on ferry boats, and they can measure autonomously all of the different parameters. So water is pumped into here. Here we have the sampling chamber. Here you can see the chlorophyll probe. There's a temperature probe in here. Salinity is measured here. Here you can see the different valves going to the different devices, distributing the water which is coming out of the keel. Here we have the peristaltic pump, and here we measure CO2. So we can measure a lot of things: sea surface temperature, sea surface salinity, oxygen turbidity, the pressure of CO2 of air and water, pH. We can measure nitrate as a macronutrient and the chlorophyll fluorescence with this device. So we switch it on in the harbor, and it measures, if we are lucky, continuously all of these parameters. All of these data are then given to the IT rack and are sent to mines. So also attached to this sampling chamber is a flow cytometer. In this flow cytometer, the water is pumped in here, and with a 488 nanometer 100 milliwatt laser, we can measure and quantify bacteria and other plankton. So that's a great device. It was built in the Netherlands. It's very robust to run on our ship. We can also make photos of bacteria and other plankton, and this is how it looks at the inside. So it's a very complicated device, but it's really very robust to run on the ship. This is a super device, and Heidi Adema is a specialist of that. It's a fast repetition rate fluorometer, which measures, with very short laser pulses, incubate with C14 on our ship anymore. We can now really measure primary production with this fantastic machine. Fast repetition rate fluorometer. Very small and very efficient. So then we have two mass spectrometers on board. This is a delta ray isotope radio infrared spectrometer, with which we can measure continuously the stable isotopes of carbon and oxygen. This is something very new, which we could not have done 5 years ago. So all of this modern technology gives us great data. And down here we have another very fine device which was built in Switzerland, and that is a mass spectrometer to measure oxygen-argon ratios, which also give a very good measure of plankton production. This device is a funny name of a mini already, very Swiss. So all of these, then we have on the other side of the ship from the snorkel, which is going into the air. We have the tubes with the air samples going into this air chemistry rack, in which we can measure, for example, aerosols, nitrous oxides, and all of these parameters of the air, which is done by our marine chemistry department in our building in Mainz. So we can also measure black carbon, which is something very important. Black carbon in the atmosphere also heats up the atmosphere. So here you can see the snorkel. So when you stand on the aft deck of the ship, we have this very high carbon fiber tube going into the air to 10 meters height, and to which the air is pumped going down to the laboratory. So this is our mast, and on top of the mast we have a PAR sensor which measures solar radiation. So solar radiation is important to know if it's cloudy or sunny or so, and we have the same PAR sensor on our water sample device going down into the water and to measure solar radiation at depth. So what we also have, we have different infrastructure. We have a fuming source, we have deionized water here, we have a filtration rack in the wet lab, and this is our IT rack which collects all of the data and sends them all back to Mainz. So this writes a continuous protocol. We have many, many data. Which we have something else which that's the wrong direction. I wanted to show you something else. Maybe here. Please start. No, we cannot see it. I hope here you can see it. That's the wrong one. I can show you later, I can show you the ship again. So on this A-frame in the back, we have a very new modern satellite communication technology, which is Iridium Certus, which is the first machines were delivered. Actually, we got the first 2 machines delivered by Iridium last year, which are now sitting at the A-frame at the back of the ship to give us a lot of satellite communication. And we have also a meteorology station on this back frame of the ship, which is run by the German Weather Service, to which we are connected to give us weather forecasts, but also to sample the atmosphere. So now we look at the global scale. So, for example, here we can see the global chlorophyll concentration. Madeira is sitting about here, very close to the oligotrophic subtropical gyres. So productivity is very low here in the subtropics, in the ocean, also in the Pacific Ocean. And what we can see here is a spring bloom of plankton in, I would guess, in about April in the northern hemisphere. So red colors give a lot of plankton productivity, pink or these violet colors give very little plankton productivity. So we are now going with our boat. We are sitting here now, Lanzarote. Today we are here on Madeira. These are our first stations to be sampled, and from mid-May we will go to the North Atlantic to sample higher latitudes. We might go, if we are lucky, if our captain says we can do it. I can sail the ship there, the weather conditions are good enough. We sail here to the west, to the east of Jan Mayen to sample in the Arctic Atlantic Ocean really. What you can see here in dark blue are the 200-mile zones. So what we try to do, we try to stay out of the exclusive economic zones of the different countries, because we do not want to ask for permission every time, which is really complicated. So we want to sample really the open ocean at different latitudes to better understand the effect of climate change on the open ocean. So we go here until about August or so, and then we need to escape from here because winter starts very early in the Northern Atlantic. We go back to Bremerhaven, to the shipyard, to get some repairs done and some renovations, and by about October we go back to Lanzarote. We might come back to Madeira, and then in the next winter season we want to go down here into the upwelling area of Cape Blanc in the Eastern Atlantic of Mauritania here. Then we will sail to the Cape Verde Islands, do an oligotrophic station here, Then we go down to the equator. The nearest island is Fernando de Noronha. It's a very beautiful island where we would have to stop. Possibly going then to Barbados to sample the oligotrophic Atlantic Ocean here. And then we need to go to a place called Bats near Bermuda. All of these stations, which I have indicated here, are long-term stations. So for example, this station here, I started sampling in 1988. So now we have a very good comparison, for example, of the past 30 years. And we can already see the effect of climate change. When we look at the foraminifers, we can see that they do change. So we will do this this year. We will also maybe do this next year and the year after. So this is our typical transects. Then we have a very special phenomenon in the Pacific Ocean, which is called El Niño. And when we have the next big El Niño, we want to go here to sample. There's a gap in the 200-mile zones between Ecuador and the Galapagos Islands. We're going to sample here, El Niño. So we have the liberty with our small research vessel to do what we want. So we do not need to ask for permission, we do not need to ask for extra money, we don't have to wait for another 2 years. We just go when we need to go. So this is what we do, and in the very far future, if we get crazy and our captain says he's up for that, actually he sailed on our ocean race from New Zealand to South America one time, 5 years ago, he told me, so he knows that ocean, and he's one of the very few people who sailed with a little sailboat around Cape Horn already. If he says it's okay, we might sail the South Atlantic Ocean. So that will be very rough, but that would be a very nice asset to our sampling. So what we want to do then is we want to better understand circulation in the North Atlantic Ocean. Here we have the Gulf Stream, the North Atlantic Current. Here we have the Canary Current, Madeira sitting here. All of this recirculation changes with climate change, and the transport of heat and humidity at a global scale is very much affected by that. So we want really to understand these systems better, and we need samples for that. Also, for example, oxygen concentration in the oceans is changing. Here we have the big upwelling areas with very little oxygen, and we can already see that oxygen levels drop in the ocean. Fisheries is affected. When there's less oxygen, we have less fish. So we will measure this. All very important parameters for climate change, and for the entire environment. So that is our aim in the near future. You are all very much invited to join, and I thank you very much for your attention. Credits to all of the authors of images and graphs which I showed in my presentation. Thank you very much. Obrigado,
Thank you, excellent presentation.
So that was very long.
No, it was...
No one fell asleep.
Yeah, I did. I was grabbed all the time, which is hard in my age. But
Says the young man.
Has anyone has questions? I have a few.
What's the operational cost of the vessel?
It's about 1,500 euros. So for maintenance of the ship, to get it run over the year, we have 500,000 euros from the Max Planck Society, which breaks down to about 1,500 per day.
And the autonomy of the vessel? How long can it stay?
That depends on the number of people on the vessel. So if we are 3 crew and 3 scientists, we have an autonomy of about 10 days.
More or less 2 weeks.
2 weeks. So when we sailed here last week, we learned that diesel consumption is very low. The ship performed very well, but we have limited space in the fridges. We have a water maker on the board, but maybe with 5 people we can do more or less 2 weeks. So we can sail to each point which I showed you, but we need to make use of all of the islands and points which are on our way. But if you ask for collaboration, you would not have to pay. That would be collaboration. We would like to work together with you, publish papers together with you, and you have to pay nothing. So Max Planck is very generous.
So in that regard, you showed some of the characterization of the bioprocesses within the different oceanic basins. Can you use the same approach, the same proxy to distinguish mesoscale features, or can you use the nitrogen as a proxy to distinguish between two different water masses, say eddies that separate themselves from the main water bodies?
Yes, you can do that. So when we were lucky in the past with the big research vessels, and I did it 2 times, we sailed across an eddy and we could distinguish between the center and the outside and also the rim of an eddy. So foraminifera assemblages change and isotope composition as well. So we can do that, yes. Of course, the lifetime of foraminifera is about 1 month, and that gives you, usually when you measure an entire foraminifera, the average concentration of the entire organism which grew over 1 month. So for nitrogen, we cannot distinguish now from one foraminifera the different isotopes. But with this nanosims and laser ICP-MS, when we shoot into the shell layer by layer, we can distinguish an eddy from the outside.
But isn't this an important topic to be focusing on, the role of these eddies in the transport of heat and salt?
Absolutely. I mean, I was in this area very often. We have this Azores current, the Azores front, from which we have eddies separating. And yes, at high resolution, we try to do everything at high resolution, and that is another purpose for which we built this ship. So we are free, if we find something interesting in the ocean, to stay as long. We have autonomy with our vessel to sample what we want to sample.
Yeah, we have plenty of eddies around.
Yeah, I can guess. I mean, you can, if you look at the ocean temperature fine scale distribution, you can see that most of the ocean is eddy dominated. The Caribbean Sea, for example, when you look at that, is a completely eddy dominated sea. And all of these frontal areas, like you are here, the front between the subtropical mold waters and the North Atlantic intermediate waters, it's full of eddies.
Yeah. Any more questions? So are you comfortable in saying that we are in the subboiling bioprovince, or because it seems to me from your distribution that we are included in the African upwelling region? Is that because of lack of resolution?
It's a resolution, yeah. No, you're not in Madeira. You're not. I mean, what we can see here is, of course, the spring bloom, which is at Madeira is in mid-March, I would say. You have the spring bloom, right?
Yeah.
In your waters here. But no, you're not upwelling.
That's right. But we do have some images that do show the Cape Gur filament coming all the way to Madeira, but they are not common. They're not very common.
No, I mean, upwelling is one thing. What we have is we have very often filaments of upwelling which are traveling very far into the ocean. So I can show you, so for my cruise planning, I found an image on the internet, very interesting, which I can show you. You can see Madeira on there. Cruise planning. So here we go. So maybe we can see it. So this here is a. So no, that's covered by clouds now. But I mean, what you can see here is, that's the same up here, that this upwelling is not a homogeneous area, but very often you have these filaments detaching from the upwelling. These are the Cape Verde Islands, and these filaments travel very far into the open ocean. So every now and then you might be hit by an upwelling filament here.
Right, true. We need more high resolution to take that. And can you use that as a proxy for the time, to resolve time, the age of these systems? For instance, could you distinguish between an eddy that is arriving, which has 3 months or 6 months or 9 months, versus an eddy that is locally generated, for instance?
That's a very good idea.
Because we have identified quite a few of those. Yeah, we have identified that some of the eddies reach Madeira from the Azores current, or from the African upwelling, and some of the eddies are locally generated. So
great.
It's an interesting spot.
It is, yes. So there are many things which need to be done, which need to be understood in a much better way.
I'm totally for these type of approaches. I'm a physical oceanographer, and the first sampling that we did in Madeira was actually with a sailing boat from the Whale Museum.
Okay.
We went to 70 miles with the fleet, we drive, this fleet around. Yeah. So we did do a lot of because as a small, not so rich country, I don't know if you know this, but the Medis and the Medis that came out of Gibraltar, they were discovered by Army, and Army is a known scientist at Scripps, and he discovered them in using sailboats during his holidays in the Algarve.
Okay.
So he used to rent sailboats, sampled these Medis at 800 to 2,000 meters depth, and then he discovered these systems here. So when I came here and we have no vessel, scientific vessel locally, but well, we can at least use a sailing ship to...
I mean, you can find them at all times. When you sample down to 1,500 meters, you cross the Medi layer, and I see them every time when I do a deep sample, I see a Medi. And
there this might also be the region where you have Antarctic intermediate water reaching the north. So
it just stops about here. Maybe we need to go a little bit further south to sample the upper rim, which is at about 3,000 meters depth here of the Antarctic intermediate water. Medis are usually traveling north, but every now and then we have a Medi traveling south, right?
Yes. Yeah, there are two branches. One that goes straight west and slightly north, and one that the south, the southern trend is deeper.
So that's the reason why we came here. So it would be great to cooperate with you. You know a lot. You're sitting in a perfect place here to do your research. Could not be better.
Yeah. I'm glad that you came. We have to talk more.
Yes.
Any more questions? No questions? You?
What is the depth range of your gear? How deep can you go down measurement?
Yeah, so that's a very intimidating question. So we have a very nice winch in the garage of our boat, and with this 6 mm Dyneema rope, we can get a maximum of 3,000 meters on the winch. But that is not easy. Winches are complicated, so we tried to get it on, and we failed. Now we have 200 meters on our winch, which is good enough to sample the upper 100 meters, because usually the rope is not standing vertically, but somewhere behind the ship. Another 1,000 meter rope has arrived in Mainz. I will bring it down when I come back on the 23rd of April, and then we try to get this 1,000 meter rope on the winch. If that runs well, we might be able to sample down to 700 meters. We could try to get the 3,000. Haley is laughing. So I sit in the garage and try to feed the rope into the winch, and Haley is sitting there with the winch remote. So 3,000 meters would be the absolute maximum if we are lucky.
But you are more interested in the upper layers.
We are also interested in, to get the top of the Antarctic waters. That would be fantastic, but I doubt we'll get it.
Yeah, if you go down to 3,000, I think you could get it.
But then we need a very straight line. So maybe if we go to the Olympic Gyre here with perfect weather conditions, no currents, flat sea, and we get it down
in a summer day, good summer day.
In a good summer day, we might be lucky to get it.
So this is an electric winch or a hydraulic winch?
It's an electric winch. So we wanted to make it hydraulic because it would be much lighter then, but for now it's electric.
We also have in the sailing boat from the Whale Museum, we also had to use an electric winch.
That was all difficult. Electricity only works for 1 month now, so we wanted to build a hybrid sailboat to produce electricity with a propeller. So we have 2 different systems and a big battery pack in the boat, which gives us now maybe 8 hours of autonomy. So we do not have to switch on the diesel engine, but it could still be better. But electricity is now running, the winch is running, everything is good, and we can sail, and we even can have a coffee on board now.
Challenging.
Everything was challenging. If you build a new boat,
Yeah.
anti-fouling was very challenging, so we tried to have an anti-fouling cover on the hull of the boat, which is not contaminating. So we found a product which is based on ceramics, which did not work. Now we have a different product on it. So we had to find a marina with a big crane, and Lanzarote in the Marina Rubicon. They have a 100-ton crane which can lift us out of the water, and then we can work on the outer hull of the boat. So, but it all needs to be done by us. It's a great project, it's challenging, and now we are very, very happy that on the way here everything seemed to work.
Is this the main motivation to make it environmentally friendly way of sampling, or is it to lower costs, or is it a combination of both?
So of course we want to be environmentally friendly, which is always good, and I mean, we are working for the environment and we do not want to pollute it. But then we want, when we sample the atmosphere, not switch on the diesel, because when you switch on the diesel, even when you open the deck house door, or when you switch on the oven, the snorkel, this air inlet, sees it within a second. So these machines are so sensitive that they can measure everything. So we try to say without contamination also of the atmosphere, and that was the main purpose.
So do you think this is a general tendency in the world to get more vessels running cheaper, or is
it is.
The tendency is to get them larger? And
no, I think there are new, now I'm alert of these sailboat projects. There's a French project called Tara Ocean. They have a big research sailboat of 36 meters length. They are doing biogenomics. They are doing a lot of public outreach. Now I heard that a group from Roscoff in Brittany in northern France has bought a trimaran to sample coccolithophore blooms, which might be interesting for you. There are some new projects with sailboats. A colleague of mine with a very small research sailboat sailed into the Baltic Sea towards Sweden last summer to collect trichodesmium blooms, I think. So bacterial blooms, to get a better idea about that. Yeah, cheap and environmentally friendly is a trend now.
Yeah, but of course the Norwegian are going into electric engines and larger.
Which is very good. I think today we have the technology. There's no reason anymore to burn a lot of brown coal, for example, or to burn a lot of hydrocarbons at all. We have technologies, and also car industries must change. It's horrible. They want to earn a lot of money, but now it's a lot of pressure on them. Also in Germany, I know it well. There's a diesel scandal, and we very soon cannot run our diesel cars anymore, which is good.
Yeah.
We must change. Germany is a rich country, and we all have enough money to make a change.
Makes sense. Well, any more questions? Well, thank you very much for coming.
And hopefully coming more often now.
Yeah.
So we are in the marina. If you want to visit us, if you're bored on the weekend, drive your car. It's nice. Have a look at the boat. It's very nice and very impressive.
Can we go visit Saturday maybe?